If you're a developer, your entire world is built on certainty, right? An if statement always leads to a predictable then. But what if it didn't? Today, we're going to dive into a world where the fundamental rules of code are kind of thrown out the window, and we have to learn to think in a completely new way. So let's get right into it. I want you to really seriously think about this for a second. Picture your code, every single conditional, every branch. But instead of leading to a definite that, it leads to a probably that. And this isn't some weird philosophical puzzle. No, this is the fundamental reality of quantum programming. We're stepping off the straight, predictable path of classical code and into a world where every single operation creates this cloud of possibilities. It's a journey into a totally different realm, one that's governed by chance and probability. So let's start with the first, and honestly, the biggest conceptual shift you have to make, moving from deterministic to probabilistic code. Getting your head around this one thing is the biggest hurdle, because it really does change how you have to approach solving a problem from the ground up. Okay, so this lays out the two worlds perfectly. Over on the left, that's classical computing. It's predictable, it's reliable, it's your comfort zone. You put something in, you know exactly what you're going to get out. But then you look to the right, into the quantum world, and everything's based on chance. You're not writing a set of instructions anymore. You're designing a system of probabilities, and the answer you get is a statistical outcome. To really understand why it's all probabilistic, we have to look at the fundamental unit of information itself. We're moving beyond the familiar bit to something way more powerful and, let's be honest, much, much weirder, the qubit. And here it is, the first truly mind-bending concept, superposition. A classical bit is easy. It's either a 0 or a 1. That's it. A qubit, though, a qubit can be in a combination of both states at the exact same time. Now, don't get spooked by the formula. Just think of A and B as the probability amplitudes. Basically, they represent the odds of the qubit deciding to be a 0 or a 1 when we finally look at it. This is the absolute best analogy. A classical bit is like a light switch. It's either on or it's off. A qubit is like a coin spinning in the air. Now, here's the crucial part. While it's spinning, before it lands, that coin isn't heads or tails. It's some combination of both possibilities at once. That spinning state, that's superposition. Only when you catch it, when you measure it, does it collapse into a definite heads or tails. And this just spells out the difference in potential, doesn't it? A bit holds one single definite piece of information. A qubit state, on the other hand, is this whole landscape of probabilities. And this ability to exist in a combined state is what lets systems with lots of qubits explore a massive number of possibilities all at once, which is where the real power of quantum computing comes from. So, if we have a new type of bit, it makes sense that we need a totally new type of logic to manipulate it. This is where your good old trusty and, or, and not gates get a serious, and I mean very different kind of upgrade. We're basically leaving the familiar world of Boolean logic and entering the world of linear algebra. Specifically, things called unitary matrices. Now, don't worry, you don't need to be a math whiz. Just know this. Instead of flipping bits from 0 to 1, these quantum gates essentially rotate the probabilities within a qubit superposition. They're gently changing the odds of it landing on a 0 or a 1. Oh, and notice that last row? Reversibility. This is a big one. And this is a massive, massive departure from classical computing. A lot of classical operations, like an AND gate, are irreversible. I mean, if the output is 0, you have no idea if the inputs were 0 and 1, 1 and 0, or 0 and 0. You've lost information. In quantum computing, no information is ever lost in an operation. You can always reverse the gate and get your original qubit state right back. Okay, so we've got these probabilistic qubits and these reversible gates. How in the world do we get a useful, actual, concrete answer out of a system that sounds this, well, uncertain? Let's walk through the process. You know, at a high level, the flow is actually pretty straightforward. You start with your qubits in a known state. Usually they're all just set to 0. Then you apply a sequence of these quantum gates, and that's your algorithm, your circuit. And then at the very end, you perform the measurement. And this brings us to the question that every single developer asks. After carefully building our circuit and manipulating all these delicate probabilities, what actually pops out at the end? This is the moment where the quantum world smacks right into the classical world. our spinning coin finally lands. That beautiful superposition collapses into a definite 0 or a 1. But, and this is the key, which one it becomes is entirely determined by the probabilities we so carefully engineered with our quantum gates. You don't get the answer, you get an answer from a distribution of possible answers. So, how do you find the result you actually want? Well, you don't run the program just once. You run it hundreds or even thousands of times. Each one of those runs is called a shot. By collecting the results from all of these shots, you build up a histogram that shows you the most probable outcomes. And this is the key. In quantum computing, your program's answer is the probability distribution itself. Okay, so let's put this all together. What does this actually mean for you, the developer, on a practical level? What are the new rules you have to play by in this new game? Here's a huge one, the No-Cloning Theorem. This is a fundamental law of physics, and it says you cannot make an exact copy of an unknown quantum state. Now, just think for a second about what that means for debugging. Your number one go-to move, just printing a variable's value to see what it is physically impossible. The very act of measuring a qubit to print it collapses its superposition, which destroys the very information you wanted to look at in the first place. So the takeaway here is pretty clear. First, you absolutely have to think differently. You have to embrace probabilities and chance. Second, your algorithms aren't simple decision trees. They're complex circuits based on linear algebra. Third, you're constantly dealing with the real-world problems of hardware noise and how fragile these quantum states are. And fourth, debugging isn't about printing values anymore. It's about using simulators and analyzing statistical results to figure out what's going on. You know, this quote just says it all. Quantum computing redefines how developers approach program design, debugging, and performance. It's not just a new language or another framework to learn. It is a complete redefinition of the entire programming paradigm from the absolute ground up. And ultimately, that's the real shift. Classical programming is all about giving the computer a series of direct, deterministic instructions. You tell it what to do. But quantum programming? That's about carefully constructing a system and then asking it a question, knowing that the answer you get back is going to be a probability. It's a whole new way of thinking, a whole new conversation with our machines. And really, it's just getting started.